Hey everybody, this is our problem about summing stuff up. You see, that's what this is all going to be about going forward, is summing stuff up. And you should say, what stuff? Exactly, that's the question. We figure out what stuff we're summing up, and then we can apply the necessary mathematics to figure out the solution. For example, we got a damn problem on our hands here. This is from our textbook. And it says, a dam has a rectangular base 1,400 meters long and 160 meters wide. The cross-section is shown. It says that the Grand Coulee Dam in Washington is roughly this size. By slicing horizontally, set up and evaluate a definite integral giving the volume of material used to build this dam. In other words, maybe we want to figure out how much dam material was required to make this dam. And while we could do some geometry in this case, we want to focus on the thinking behind the calculus, so bear with me. So the front of this, like the water's coming here, hitting the dam. This is just the cross-section of it, is this trapezoidal shape. And we want to figure out by setting up an integral, by summing up some stuff, we want to figure out how much volume of material we have in this dam. So, what do I mean by summing up some stuff? Can you imagine this? A horizontal slice, they say. Consider a horizontal slice. Can you imagine a slice of material here that's infinitesimally thin? Now, I hope this sounds familiar to you after your time in calculus. We like, in calculus, to break things up into infinitesimally small and have infinitely many of these things. And this is a prime case of that. If we have an infinitesimally thin slab of, say, concrete, as this dam is made out of concrete, let's just say, this infinitesimally thin slab of concrete, can you imagine finding the volume of it? And find the volume of the one right below it, the one right above it, below it, above that, below it, above that. All infinitely many of those infinitesimally thin slabs of concrete. Let's find their volume. Sum up the volumes, bam, we get the volume of the overall dam. So, what is the volume of that thing? I hope you can see, even from my rough drawing here, that infinitesimally thin slab is a rectangular slab of material, concrete, let's say. And the volume of a rectangular slab of concrete would be found by taking the length times the width times the height. Now, can you imagine, again, doing that infinitely many times for each of the slabs from the bottom to the top, summing up all those volumes, getting the volume of the entire dam. Now, this length is measured in meters. This width is measured in meters. This height is measured in meters. Meters times meters times meters. Cubic meters of volume. Yes, that's exactly what we would want. So what we're going to do. So the volume of this thing is going to be found by taking the length. Now the length, I'm going to call this dimension the length. The length is 1,400 meters. And that 1,400 meter length is 1,400 meters no matter where I slice it. This bottom slab of concrete has a length of 1,400 meters. This top slab of concrete has a length of 1,400 meters. No matter where I slice it, 1,400 meters. Now what about the width? The width of a slab is not always the same. The width is this dimension here. At the bottom, 160. At the top, 10. But that width is always changing depending on where I am inside of this dam. And so we need to have some way of acknowledging how that width changes. Now what I'd like you to consider is a graphical representation of what's happening here. The width varies depending on if I'm at the bottom or the top, depending on the height that I'm talking about. Now, when the height is 0, when I'm at the bottom of the dam, that width is 160. Could I say it this way? When the height is 0, the width is 160. And also, when the height is 150 meters, remember the height of the dam was 150 meters. When the height is 150, the width is 10. And so we have a couple of data points here. When the height is 0, the width is 160. And when the height is 150, the width is 10. And we might imagine, due to the structure here, that as the height changes, the width is going to get more and more and more narrow. The width is going to get more and more narrow in this linear fashion, due to the sides being nice straight sides. So we have a linear function here. So width is a function of height, and that width is with that intercept of 160. When then we subtract some amount. The amount that we're subtracting is this. Notice that we go down to 10. That's a change of 150 meters. And a change of 150 meters, rise over run, 150 over 150. This thing has a slope of 1 meter of height for every meter of width, or 1 meter of width for every meter of height. So this thing is a minus 1 times h. We subtract 1 meter of width for every 1 meter of height. Now just to kind of get a sense of this, when h is 0, 160 minus 0 is 160. Yes. When h is 150, 1 times 150, 160 minus 150 is 10. Yes. So this is a wonderful function to measure how that width changes relative to the height. So the width of this thing, 160 minus h. Nice. Now what about the height? The height of one of these slabs. Remember, the height we're talking about here are these infinitely many, infinitesimally thin slabs of damn material. So we want to figure out this thing right here. Well, it's infinitesimally thin. And so this is our little change in h, our little delta h, just like you've seen with integrals all along. We have infinitely many rectangles, little delta x's, infinitely many, infinitesimally thin. This is just infinitely many, infinitesimally thin changes in height to get the volume of that slab. So this is a dH. So all together here, the volume of a particular slab is 1400 times 160 minus whatever height level we're at times that delta H. This is a representative volume of any slab. Now, what is calculus for but summing stuff up? What we want to do is sum up the volume of each and every one of those slabs. We want to, I guess I'll go over here, to get the overall volume of this damn material, we want to sum up all of those Now, look at the dH. So we're doing this integration with respect to h. So h varies from the bottom, height is 0, to the top, h is the 150 meters. So if we integrate this from 0 to 150 meters, we'll get the overall volume. Hey, just one more quick unit analysis. Remember, this 1400 was in meters. This 160 minus h coming from the width is in meters. Even this little delta h, this infinitesimally thin delta h change in height is measured in meters. Meters times meters times meters. Whatever we get here is going to be in cubic meters. Hey, pause the video. I didn't really pause. Pause the video and try to go do this integral. And after you've tried it, get out some paper and some pencil. Don't just sit and watch me do all the work. Get a piece of paper and pencil out and try to integrate this thing. When you come back, I'll do it too, but pause and you try it first. All right, what I would do here is, first of all, recognize the 1400 is a constant multiplier. So 1400 times the integral, really I just have 160 minus h dh from 0 to 150. So what I really have here is 1400 times. Now, let's talk about the antiderivative of 160 minus h. What did you take the derivative of to get 160? 160 times h. What did you take the derivative of to just get h? 1/2 h squared. Remember how derivatives work. The 2 comes out front, dies, decrease by 1, just get your h. Plus c, really, but it's not going to matter because this is a definite integral. We're going to integrate this thing from 0 to 150. Hey, I'm going to come back over here just in case. If I'm off the screen right now, I'm going to be sad. So I'm going to come back over here and do my fundamental theorem of calculus. We've got 1400 times 160h, where h is 150. Minus 1/2 h squared. Minus, plug the 1400 in. Now you plug in 0 for h. Now if you plug in 0 for h, 160 times 0, 0. Half h squared, 0. It's all going to be 0, so all of this is going to be 0. Hey, also, by the way, the plus c's really don't matter because when you plug in the 150 for h plus c minus, when you plug in the 0 for h, you'll subtract that c, and the c's will go away anyway. So it all comes down to this. What we really have is 1400 times 160 times 150 minus 150 squared. This thing here is 0. Let's see what it comes out to be. Hey, you should be calculating too while I am. Come on, come on, come on. 1400 times 160. Whoa. 160 times 150 minus 1/2 times 150 squared. Boom, boom. I get 1785000. Boom, boom. 17,850,000 cubic meters of dam material. That's a lot of dam material. Also, it took a lot of dam workers to build that dam. But you gotta hold back the dam water. It's very important. I hope you see how knowing what that geometry is, the geometry of that rectangular slab, we can now sum up with integrals. We can sum up infinitely many, infinitesimally thin, and determine things like volume. Go try it.